Hi, my name is Shri. I'm a junior in computer science, and for Deep, I was able to create a demo demonstrating the ideas and principles behind quantum computing and create a demo that allows people to explore what quantum circuits really are, how gates work, how they compare to, regular classical computers, and showcase a little bit into how qubits work and some of the math behind it in a way that's somewhat digestible. So I will now show you an actual demo of the interactive product. So here is the interface of the application. Here we have the list of quantum gates that I personally programmed in, along with the ability to add or subtract qubits. You can see the qubits on the main screen here, and you have these columns to effectively symbolize where you can place each qubit or each gate. And then here we have a diagram that'll showcase either the state vector probabilities or the actual measurement probabilities as applicable. And here we have the block sphere visualizations. So I can first example put a Hadamard gate here, and then I can click simulate. Now once I click simulate, you can see that I have an opportunity of either getting a 0 0 or a 1 1, because obviously I have no qubit in the Q0 slot, so this will always be a 0. But I have a Hadamard here, so there's a 50-50 on whether this qubit will be a 0 or a 1. And then you can see here in the block sphere visualization, which is a little bit finicky, I have that this Q1 with the Hadamard is in the superposition state between the 0 and the 1. And then I also have for Q0 just a standard arrow pointing towards 0 because that's all it is. Now I can add more gates. Here's an example of a 2-qubit gate, the CX. Now what this does is a controlled NOT gate. So if the target qubit, this one, is a 0, then it does nothing to the second qubit. But if the first qubit is a 1, then it flips the other one. So when I click simulate here, I can go by step execution. So after the first column is executed, we have, as seen previously, the Hadamard coming into effect. And then the next step would be the control knot. So this puts us in the entangled bell state, as is commonly known as, which means the two qubits can either be a 0 0 or a 1 1. And then I also have measurement gates as well. So if I click simulate here, and then I go to the measured, you can see the measured outcome probabilities. So this is a really cool demonstration that I was able to make so that I could showcase how quantum computing even works and how these circuits are visualized and give the average user a little bit of an insight into this exciting technology.